Good morning, everyone. Hope everyone is doing well. Happy Wednesday. Happy second lecture of the quarter. So before we get started, let me just point out a few things. So just a reminder. So there's no lab today. So we start labs next week. So labs start week 2. And so what I have done, so if you go now to our class page, so content, and under the 105 labs, I've started uploading. So now I have the ELISA procedure up for y'all. So I have it in PDF and Word document. Oh, I did not want the Word. Let me show you the PDF. So I have a PDF of the lab up there. You can look at it. So today I'll be filming a video, so hopefully the video will be up shortly for those of you doing the online portion. But this lab I wanted to mention because you could actually do this at home if you wanted. So the reagents are shortening, so vegetable shortening oil, coconut oil, olive oil, and then just distilled water, and then this sodium hydroxide. So this is food grade sodium hydroxide. So if you wanted to make your own soap at home, you can get this off of Amazon, relatively cheap, and then some essential oils of your choosing. And then you would just need to have some glassware that you could use at home, and then just follow the directions. So you kind of melt everything together, and then, so those are your oils that will undergo saponification. And so you dissolve the sodium hydroxide. Of course, you just want to be careful because dissolving sodium hydroxide is exothermic, so the temperature is going to be rising pretty quickly, probably, close to 100 degrees Fahrenheit or so. So you just want to add that carefully, especially if you were doing this at home. And then get that all nice and dissolved. Then make sure they're around the same temperature. So about 45 degrees Celsius or 100 Fahrenheit. And then add them together, start stirring. So you'll have add your base to your oils, then that'll start the saponification reaction and it'll begin thickening. And so there's two different ways to do it. If you wanted to do it the cold soap method, you would stop here and then you pour it into a mold, leave it for 24 hours, then come back and let it cure for another 6 to 8 weeks. In lab, we're going to try the hot method. So after it gets pudding-like, then you continue to heat it up until it looks clear, a little like Vaseline. Then you add your oils, your color, your fragrance, stir that up, pour it into molds. So we'll be doing that in lab next week. Or like I said, you could actually do this one at home, and there'll be a video available if, of course, you're not comfortable doing it at home and can't get the reagents. All right, so did anyone think about nuclear power, what you know, what you don't know? So we had started talking about it. So we kind of mentioned that we had to have kind of this critical amount of uranium for this reaction to go. And so now let's kind of take a deeper look into how nuclear power compares. And so once again, this is the fission reaction. So we're splitting atoms, so they're becoming lighter. So they use fission to generate electricity. So according to this, about 20% of the electricity is generated this way. And so most reactors use uranium-235, like I kind of mentioned on Monday. Kind of the new technology is to take that uranium-235 and then it gives the byproduct of thorium. And so now they want to use the thorium. And then so what happens is this nuclear reaction goes, it produces a lot of heat. That heat then boils some water, which turns into steam, which turns a turbine. And so what I wanted to talk about is kind of this concept of energy density and how, nuclear power compares to other sources of power. So let's look at this comparison here. So we have nuclear power plants. They use about 50 kilograms of fuel to generate enough electricity for 1 million people. And then there's not air pollution. Of course, it doesn't mention, the waste that is generated, but generally the waste from nuclear power plants is relatively small, and these facilities are able to store them themselves. So compare that to coal burning. So this takes 2 million kilograms of fuel to generate enough electricity for 1 million people. So that's a huge difference. So that's 50 kilograms versus 2 million kilograms. And so coal, the problem with coal is, especially if it, maybe you heard the term dirty coal. That just means that it has more sulfur impurities in it. And so those impurities can lead to all these sulfur oxide species. And then you also get NO2 and of course CO2. But my main interest is this kind of energy density. So that's something that I wanted to bring up, is energy density. And so that is a big advantage that nuclear power has. And so these nuclear reactions, right, they release a lot more energy than just a chemical reaction. And so all that energy can be used to heat and power. So let's look at another. So I pulled up some other statistics just so we could compare it to other sources. So again, this is kind of energy density with different fuel types. So wood versus coal, all these diesel, gasoline. But look at the energy difference, the energy density difference. So all these, sources that we usually use, again, all these burning. So burning these is a combustion reaction. So you can kind of tell, again, the difference in energy between a chemical reaction of combustion with, again, extremely low energy density compared to uranium, where it's a nuclear chemical reaction and much higher energy density. So that's really the big advantage that nuclear has. So the other thing that you can think about is just like its footprint, like environmental footprint, how much space a nuclear reactor takes up and its waste versus, I'll compare it to solar and wind at this point. Sorry, my cat is blocking my screen. There we go. So other things to think about is just environmental footprint. So again, I think that the nuclear reactors have some sort of advantage, and they're relatively small compared to, at least size-wise, compared to, let's say, versus a solar farm. So a solar farm, right, that's a lot less energy dense. You would have to have all these solar panels spread out over a large area. And so that's something that, environmentalists have been concerned about, is that solar, even though it seems attractive because the sun's always shining down on us, so all this energy is constantly beaming down on Earth, but of course that energy is very diffuse. It's spread out over a large area, so we have to capture it over a large area. And so that can just leave a huge footprint. And so that could impact wildlife. People have been concerned that this also impacts like migration patterns, or it hurts like birds flying overhead, versus, again, a nuclear reactor that's a lot small and just has, right, a small building. And then that waste can be stored at the facility or reused. And so continuing to look at these nuclear power plants, so the fissionable material, so the uranium, is stored in long tubes called fuel rods, which are arranged in a matrix. And again, so those are the subcritical level. And then between the fuel rods are control rods made of neutron absorbing material. And so these neutrons are needed to sustain the chemical reaction. And then these rods are placed in a material called a moderator to slow down the ejected neutrons. So this is to keep this chain reaction just below that critical mass, because you wouldn't want this nuclear reaction to go out of control, right? So once you have that critical mass, now you have this chain reaction that's just going to go off again, just like the bomb. We don't want that in a nuclear reactor, right? We want it controlled. So there it is, kind of all kept under control. And usually all these things are kept under, like passive control. So if there's in an emergency, everything kind of shuts down. And then, I'll mention Fukushima. So, what happened there with that power plant is they lost power, and so the waste was stored underwater. But since, something happened with the power, that caused the cooling to fail. And so it was the waste that kind of got out of control. But I think, since that, they're always redesigning these nuclear power plants to make them safer, since, they do get a bad rep, especially, from Chernobyl. I think there's a lot of fear from that. But that's really not the case. So, people are working to make investments in nuclear power. I generally don't like Bill Gates just because I'm suspicious of his motives. But his company, TerraPower, has been doing some cool, innovative work. So that seems promising, at least, if you are worried about energy sources and fueling the earth. And, if you are worried about our environmental impacts, I think nuclear energy is a great way to decrease it. All right, so last topic here is nuclear fission or fusion. So now we have fusion, so fusing together, and so just like you would expect from its name, fusion is the combining of light nuclei to make heavier, more stable nuclides. And so this is what the sun does. So the sun uses fusion of hydrogen isotopes to make helium as a power source. And so this is a high input of energy to initiate the process, because you have to overcome the repulsion of positive nuclei. And it produces 10 times the energy per gram as fission. So even more energy. And unfortunately, the only currently working application is the H-bomb. So scientists are currently working to make fusion a source of power. So if we could do this, on Earth, that'd be really cool. We could get a lot of energy. And it would be even more energy dense than these nuclear fission reactions. But, obviously there's some barriers to overcome, especially this, how do you initiate this reaction in a controlled manner that is sustained? All right. Any questions on the chapter? I wanted to go over a few things from the homework next. Probably go over the homework. So before we do kind of these half-life problems, I want to hit just like the trivia and things that you might need to know. So a lot of these, comparing in terms. So I think this is relatively easy. So we have our alpha particle, which is of course our helium, versus our beta particle. So as our electron. And then electron and a positron. So a positron is the anti-electron. So massless with a positive charge. Trying to remember what was. Just making sure they used an E. So fission is splitting atoms, fusion combining. And then let's see. I'm looking in your book for rad and rim. There we go. I knew I was just blind. So it's under page, at least on my book, page 238, section 10.4. B, it goes over rad and rem. So rad is radiation absorbed by 1 gram of substance. And then rem, if you remember, that was kind of the people equivalent. So radiation measurement, so absorbed by man. So, and the LD50 for humans for rem is 500 rem. And 600 rem is fatal. So remember, LD50 is kind of what level kills 50% of the population. And then the PET, remember that was positron emission tomography. So using the positron radiation for mapping. And so some isotopes, so this might come up on the exam or like quizzes, I mean. So carbon 11 is used, oxygen 15, nitrogen 13, and fluorine 18. And so CT, so this uses radioactive nuclides, and CT does not. So this is computed tomography, and this uses X-rays. So a little bit different than using a radioactive isotope in your body. And then, so MRI. So MRI stands for magnetic resonance imaging. So it basically uses a huge magnet and radio waves for imaging. And then looking at 4 here, so we didn't go over this explicitly, but I at least wanted to mention kind of what this M meant. So this M means metastable. So it still is, it is radioactive. And so it is used. So it's one of the most used radioactive isotopes for imaging and diagnostic purposes. So it's apparently used a lot for SPECT, so single photon emission computerized tomography of brain, bones, blood, kidney, thyroid, heart, gallbladder. So a lot of things. And it's desirable since it has a 6-hour half-life. And so what type of radioactivity? So it emits gamma rays. All right, so I think I want to go back and look at these math problems now. So let's look at the half-life problems. So we have, and I mentioned that we were going to do a bit easier half-life problems. And so let's kind of go with how to set these up. So question in the chat for beta emission, would you prefer the E subscript over the beta symbol? I guess it really doesn't matter, to be honest. So the thing that you want to be aware of, so I'm going to go back over here, because using that beta symbol, right, that's not wrong. But the only reason why you'd want to, show the other way with the 0, -1e is because when you're balancing these equations, right, writing it over the z -1e will help you, understand what your other product is. And so your second part is you're asking because the positron emission also uses the E symbol. So yes, so that's part of kind of the confusion, and that's why you might see beta decay referred to as like negative beta decay for just our beta decay, and then positive beta decay for positron emission. So did that clarify your question? So let's, and feel free to keep interrupting with questions and everything. Now is the time to get anything clarified while you have me live. And I do have office hours after this as well. All right, so let's take a look at these half-life problems. And so we're not going to face, some of those crazy, I shouldn't even say they were crazy, but we probably won't have problems like this, even though I still want to go over a couple of these more difficult problems so we know how to do them. But let's go over the types of problems you'll actually see. So this is from your homework. So we have carbon-14 has a half-life of 5,730 years. How long will it take for a 5 milligram sample of carbon-14 to decay to 1.25 milligrams? And so let's set this up kind of the simple way. So we just start here with 5 mgs. And then, so this is, right, my number. Let me set this up a little bit better. Welcome, Lionel. So we'll start at kind of number of half-lives. So 0, and then amount. So we're starting with 5 milligrams. Then our first half-life, we lose 50%. So now we're at 2.5 milligrams. Second half-life, half that again, so 1.25 milligrams up. And look, we're there already. So now, all we have to determine is, okay, we did 2 half-lives. And so We can just take this number, multiply it by 2. You can also kind of write it down. And I'm going to bust out my calculator for this. So 5, 7. Oh, helps to turn it on. 5, 7, 3, 0 times 2. And so that is our answer, 11,460. So again, I'm just expecting you to use these nice even numbers, so we didn't have to do anything crazy. Just kind of go through our calculations like that. Now we have, so iodine has a half-life of 8 days. So what fraction of sample of iodine 131 will remain after 32 days? So looking at this question, so they told us how much one half-life is. And then if it's 32 days, so how many half-lives did we go through? If you're in the chat, let me know you're alive. So we could take our 32 divided by 8, right? So we have our total number of time divided by how many half-lives will happen. So 32 divided by 8 tells us that 4 half-lives will occur. And so now let's just do this kind of simply. So we could start off, thanks Ashley in the chat. So 4. So we start off with 100%. And then after 1 half-life, we're at 50, 2, 25, 3, 12.5, 4, 6.25. So there is our answer. So 6.25%. So the other thing that you could do if you wanted to know what fraction is, so you have your number of half-lives, and then you could take it to the power of how many half-lives occurred. So 0.5 to the power of 4 also gives you 0.0625, which we can change to 6.25%. So either way, you'll get that answer. So let's try number 4. So tritium, so this is our H3, has a half-life of 12.3 years. How much of a 10-gram sample of tritium will remain after 24.6 years? So I'll give everyone a few minutes to work through this. Put on some music. So let me know in the chat what your answer is or how it's coming along, any thoughts you have. and I'll start going over it as well. So they gave us the half-life again, and we had 24.6 years. So how many half-lives occurred? Of course, divide. And so we should get 2 half-lives. And then, so how much of our 10-gram sample will remain? So there's 2 things we could do. You could kind of make this cheat sheet. And so, let's talk about the exams, kind of what's expected. So, of course, you're doing these exams, from home. And so the resources are all available to you. So internet, book. I would just suggest, of course, because the thing that's going to hurt you on a test is time. So you want to make sure that you have any information you need ready to go. And so that's why I kind of suggest if you make this little cheat sheet for yourself, so okay, at 0 half-lives, we have 100% of the material. At 1 half-life, 50% to 25, etc. So now if you have this cheat sheet here for you, you don't have to go through it every time. So looking at question 4 here, I'm looking at my cheat sheet. I know that after 2 half-lives, 25% of the original parent material will be there. So I can just take 10 times my 25%. So that gives me 2.5 grams remaining. You could also, work it out kind of more slowly. So you could do 10 grams after initially, 5 grams after 1 half-life, and then 2.5 after 2. So either way, you get the same answer. Let's try number 5. So polonium-214 has a half-life of 1.6 times 10 to the negative 4 seconds. How much of a 1 gram sample of polonium-214 will remain after 0.64 milliseconds? How much will remain after 2.56 milliseconds? So take a few minutes, then we'll go over it. So what are some things that we need to watch out for when looking at this problem? So they gave us the half-life in seconds, but then they were asking us this in milliseconds. So let's go ahead and convert this right to milliseconds. And so, 1.6 times 10 to the negative 4 seconds. I want to go to milliseconds. So 1 second on bottom, or 1,000 milliseconds in a second. Now we can just multiply it. So this gives us 0.16 milliseconds as our half-life. So now, how many half-lives will occur? So let's just divide. So 0.64 divided by 0.16. So how many half-lives does that give us? So just divide. Again, let me know in the chat what you're doing, how you're doing, your answers. Oops, did the opposite. So we get 4 half-lives. Sorry, I plugged in the answer instead of... So I would go back to here. So we have our 6.25% again. So if we have a 1 gram sample and we want 6%, so we have to take 1 gram times 6%. So that gives us 0.0625 grams left. And so how much will remain after 2.56 milliseconds? Well, let's bust out our calculator again. So now we have 2.56 divided by 1.16, sorry. So now we get 16 half-lives. So 2.56. So now this may be a lot to do by hand, but we can figure out how much percentage will be remaining if we take 1/2 to the power of 16. So let's do that. So 0.5 to the power of 16, right? Since we're just halving things. And so now that's really small. So that's a percentage. So times 1, of course. And so our answer is extremely small. So 1.53, well, actually 1.5, because I only have 2 sig figs. So 1.5, I didn't pay attention, times 10 to the negative 5 grams. So that's probably at least the hardest problem you should see in this sort of half-life sense, where it would be hard to do it, you know, by hand. You could do it by hand, but that might be easier. Any questions on half-lives or anything? So let's look at some of these other questions. So I highly encourage you to participate if you're in the chat. And so let's look at this one. So phosphorus 32 decays by beta emission. So what's going to be the product? So put on our thinking music for a little bit, then we'll go over it. All right. So what is our answer for A? Do we get an answer? So we had our beta emission. So let's start writing out. So we have phosphorus, 32. You need to remind yourself, right? Phosphorus is 15 there. So if it decays by beta emission, so that's that 0, negative E. And again, I'm only using this so I can balance. And so now I'm going to make sure that my top numbers are balanced. So that makes whatever our product is have a mass of 32. Then we have a negative 1. So that's going to make this 16. And we can always go back over. So element 16 is sulfur. Let's do the next one. So iodine 131 decays by beta and gamma emission. And so feel free, type your answer in the chat. All right. So for this one, I'll just start writing iodine, and then I need to look up what atomic number it is, so 53. And it decays by beta and gamma emissions. Remember, gamma just releases that energy, so I'll just write the symbol for gamma. And then plus beta, so I'm going to write it as 0, negative 1e, so I can determine the products. And so our product would have a mass of 131, but then it's now element 54. Again, balancing out this negative charge. So looking for 54, so now we have xenon there. Any questions on those? So let's just keep going through the rest. So we'll do radium 226. So radium, I'll just start setting it up again. So make sure you write the correct symbols because you have radon and radium. So make sure you don't confuse them. So radium is Ra with 88. And then again, it decays by alpha and gamma. So I'll write my symbol for gamma. Alpha is that helium atom. So now we can balance it. So 226 minus 4 gives me 222. So notice my mass is all balanced. And then now 86, I believe that's polonium. Oh, no, I was wrong. Radon. So now radon. And then this leads us into this next one. So radon 222 then decays by alpha emission. So take a minute, solve that. So now we have our alpha emission. So I'll just start by writing what alpha is. Now I'll do the same thing. So 222 minus 4. What does that give us? So 218. 86 minus 2 gives us 84. But no, I think that's polonium. Yep. So polonium. So let's do these last three. So let's start with carbon 14 decays by beta emission. A lot of beta emissions. All right. Welcome, welcome if you're in the chat. So carbon 14, just writing that down. So it decays by beta emission. So once again, we'll write it as such so we can balance it. So by total mass, 14 is still our total mass, but now our identity has changed to to 7 to balance out this -1. And so that gives us nitrogen. So see if you can do tritium. I think the trickiest part is how do you write tritium? All right, so let's look at tritium. So this is hydrogen 3, which means it has a mass of 3. And then, so it's still element 1, so we put our 1 there. Then it decays by beta emission. So mass of my product, still 3. But now we have a -1 there. So that's going to make this a 2. So we get 2 plus -1 gives us back to 1. And so that's going to give us helium-3. All right, last one. Give people a few seconds to write it out, and we'll go over it. So now last one, so cobalt 60. Let's look at what, so cobalt is 27. So again, I'll write my gamma symbol plus beta. And our other product has a mass of 60 and atomic number 28. So that brings us to nickel. Oops. All right. So I think that pretty much sums up what I wanted to go over today. Trying to think of anything else. So I think the rest I can kind of leave for y'all, unless there are pressing questions, but most of these you can look up, and I'll let you look that up so you can remember that. So let's go ahead and end here for today. If there are any questions, just let me know. I'll be hanging out on stream for a few minutes, and then I will also have office hours. So if you would like to see me in office hours, just email me. It's going to be through my Zoom link, but I realize I don't think I posted that on the syllabus. So just email me. I can send you my Zoom link, and I'm free to meet, after class as well. So thank you for being here, being live, asking questions, participating. That's awesome. Just keep it up. And I look forward to seeing you all next week. So again, no lab today. So lab starts next week. So thank you and have a good weekend.